Hello friends. Friends, today we will discuss Gauss Law for electrostatics, its derivation, applications and limitation. So let us first discuss about what is the statement of Gauss Law for electrostatics. Now, what is the statement here? The statement is the total electric flux, the total electric flux through any closed surface. The total electric flux through any closed surface is equal to 1 by epsilon naught times the total charge enclosed by the surface. That is, flux is represented by phi e. This equals to closed integral of E dot ds equals to q by epsilon naught. Now, again, what is the statement? That is the total electric flux. This is the flux through any closed surface. Now this is the closed surface ds. Okay, through any closed surface is equal to the 1 by epsilon naught times the charge, 1 by epsilon naught times the charge enclosed in that surface, the charge enclosed in that surface. Okay, now this is the statement and this is the mathematical equation of that statement. That is, the total electric flux enclosed in that surface equals to 1 by epsilon naught times, that is in the free space, charge enclosed in that surface. Now let us start the discussion about this. Now suppose here is a charge, and because there is a charge, there will be electric field due to this charge. And what Gauss suggested, that to calculate the electric field due to this charge, there must be a Gaussian hypothetical surface of any shape, of arbitrary shape. Now if suppose here is a small portion of this particular surface, here is a small portion ds, okay, and suppose electric field due to charge q passing through this surface is E. Electric field passing through this surface is E. Electric field due to this charge is, suppose it is E, and just to give the symmetry of this shape, and suppose, and it is not suppose, what will be the direction of this area element? My dear students, always remember that the direction of the area element, suppose here is a cylindrical surface, just for example, the direction of this upper surface area element will always be outward, and direction of this will be again outward. Okay, perpendicular, normal to this surface, this is outward surface. Okay, so here the direction will be again outward of this area element. Okay, so from this area element, small area element, if the small amount of flux passing through this area element will be equals to E dot ds. I have already discussed about electric flux. in my previous video lectures. E dot ds. Now, what is the direction between E and ds here? The direction is 0 degree. So E dot ds by vector law, this is eds cos theta, and here the direction is eds cos of 0 degree, because both are in the same direction. Both are in the same direction. So cos of 0 is 1. So it will become eds d phi equals to eds. Okay. Now this is our equation number 1. So small amount of flux passing through this surface equals to d phi is equals to eds. Okay. Now by definition of electric field intensity, E is equals to 1 by 4 pi epsilon naught q by r square. Now r is the radius from this origin O. Suppose here is point P, from O to P it is r. So E is equals to 1 by 4 pi epsilon naught q by r square. So total flux, if this is a small amount of flux passing through small area eds, then what will be the total flux? The total flux will be phi is equals to integral of E dot ds. Okay, this will be the total flux. So total flux equals to phi is equals to, if I change it to phi is equals to integral d phi equals to E dot ds. So by integral of d phi we will get phi. So phi is equals to E dot ds, and this equals to eds from equation number 1. Okay, if I remove the sign of vector eds. Okay, so phi will be eds. Now if we put this equation number 2 in this equation eds, then phi equals to 1 by 4 pi epsilon naught q by r square, and in the last here it will remain eds integral, because we will solve it later on. Okay, so integral of d phi. Now I will repeat this step again. So d phi, we have solved it above eds. If we want from this equation the total flux, total flux will be integral of d phi equals to integral of eds. So integral of d phi will be phi equals to eds. Okay, so if we put the value of E here, it will become 1 by 4 pi epsilon naught q by r square ds. So this will be 1 by 4 pi epsilon naught q by r square integral of ds. Now Gaussian surface, suppose it is a sphere, so integral of ds will be, what is the area of the sphere? It is 4 pi r square. So 4 pi r square cancel out. So flux equals to eds equals to q by epsilon naught. These are the closed surface integrals. Okay, so this is the derivation of Gauss law for electrostatics. Phi is equals to integral of E dot ds. After solving this, we will get q by epsilon naught. This is about the derivation. Now what is the application? What is the application part? We will discuss in detail in other video lecture, but it is used to determination of electric field in some of problems in which the object possesses spherical symmetry, cylindrical symmetry, planar symmetry, or combination of these. So if we know the symmetry, we can, and if we know the charge distribution, we can calculate the electric field. And what is the limitation? What about the limitation? Limitation is that Gauss law cannot be applied on non-Gaussian surfaces. Non-Gaussian surfaces. It can be applied only if the surface encloses, if the surface encloses the volume completely. If the surface encloses volume completely. This is the limitation of the Gauss law. I hope so. You have understood about this, the Gauss law derivation, application. We will discuss in the later section, and the limitations. Thank you.